Okay, so in this video we're going to look at a kind of a tricky subset of rotation, and that is banked turns. So if you think about when you're exiting the freeway or getting onto the freeway and you make a really sharp turn, you're kind of going, I think you sometimes will go like 270 degrees in a circle, and it's a really tight turn. And if the ground was just flat, you would not be able to make that turn. But because the surface is banked, looking from the side, it's at an angle, then it actually increases the speed at which your car can take that turn. And so that's going to be the focus of this video, is why that is and how to analyze that situation. Okay? Basically, what's happening is your car wants to go in a straight line, okay, because of its inertia. And if you have a turn, then the car has to, if you're going to turn the car, then the friction between the car's wheels and the road have to push it in a circle. And that's fine, but there's a limit to how much friction can push it. Now, if it's a banked turn, and so you have some kind of like banked track like this, then when the car makes the turn now, the car still wants to go like in a straight line, but instead of friction being the object or being the force pushing it inward, the normal force from the track is actually what's pushing it inward. And so that normal force from the track that's pushing the car inward is much, much stronger than the amount of friction that would be required to, or it's capable of providing much more force than the friction between the tires and the road. And so you can be going much faster and have a safe turn when it's a banked turn than if it's a flat turn. Okay, so this is what we're going to be analyzing. And we're going to actually start off with an airplane example, because I think it's a little bit simpler. So here's an airplane making a banked turn at some angle. You got the wings, you've got the tail, and you've got the propellers here. And I've drawn like a little small prop plane, but these numbers are more for like a jet. So what we're going to do is we're going to draw a free body diagram. And so we have weight, and we have normal force at an angle. Actually, in this case, it would be lift. And there's no other forces. Okay, that's it. That's all the forces acting here. But there's something you have to be really careful about. So it's easy to confuse these with those sliding block problems that we've done. But in this case, the acceleration of the airplane is towards the center of the circle, not down a ramp. Okay, and what that means is the only acceleration is in the direction of this radius. In the up and down direction, it's balanced. Okay, which means that for lift, the y component of lift is basically balancing out gravity. And then you have this x component of lift that's causing the rotation to occur. Okay, that's causing the centripetal force. Okay, and so this is again kind of different from the block sliding down ramps, because in those cases the y component of the normal force does not balance out gravity, and that's why we have to rotate the coordinate plane so that we don't have acceleration happening in two directions. Okay, so anyway, to figure this one out, we're going to say the sum of the forces acting in the direction of the radius, since it's rotating in that direction, are going to add to be mv squared over r, and that's going to be just for that angle right here. So we're saying that this angle is theta, okay, which means that if we can draw a 90-degree angle here, then this would be the complementary angle. So this angle right here would also be theta, which means that the inward component, let me draw a little bit bigger. So we have lift acting at an angle, we have if this direction is horizontal, and this is the angle right here, and this direction is vertical, then this would be the complement to that angle, and so this would be the same as angle theta, which means that the inward part Lx would be L cos or L sine theta, and the up and down part would be L cos theta. So we can say mv squared over r equals L cos theta, and that's our net force in the direction of the radius. And we can do net force in the direction of y, and here the forces are balanced. 0 equals upward L, sorry, this one was L sine theta, I apologize, because that was this one right here. And so Ly would be L cos theta minus mg. So what we can do here, I'm going to add mg to the other side, so we get mg equals L cos theta. And the easy way to solve this is just to divide them, because we know that sine over cosine is tangent. So if we're solving for what the angle is, we can divide this equation by this equation, and we can get tangent theta. So we'll say mv squared over r equals L sine theta, and then we're going to put mg right here and L cos theta right there, and so those L's cancel out, and we're left with tan theta over here, and the m's over here cancel out. So we get v squared over g times r equals tangent of theta, and then we can plug that in to figure out what that angle would be. So we get an angle of about 22 degrees. Okay? And so basically, if for an airplane to make this turn 123, if it's going 123 miles per hour and it's going to make a turn with the radius of 3,800 meters, it would need to have an angle of 22 degrees to maintain its altitude. If that angle was, if it was at a steeper angle, then I believe the normal force would be too small and it would start to drop. And if the angle was too flat, then it wouldn't be able to make that turn. So here we have a car, and the car is going on a bank turn. And so again, if you think about this bank turn, you have the car on it, and the car wants to go straight, and the turn is kind of forcing it inward with the component of its normal force along the radius. So if we draw a free body diagram, we have the weight and we have the normal force. Okay, and in this particular case, the magnitude of the normal force is actually stronger than the weight because it's causing it to accelerate. But the y component, remember, is balancing out gravity. And so this is mg, or Fn cos theta, whereas this one was Fn sine theta. Okay, so to solve this, we want to know how fast this car can make a turn that's banked at 30 degrees with a radius of 316 meters. So this would tell us like how fast the car should go to safely make this turn. And this is even assuming that there's no friction. Because if there's friction, it can even go faster. But we're not going to worry about that right now. Okay, so again, like before, we'll do a net force equation for the direction of the radius. So since it's rotating in that direction, we can say the net force is mv squared over r. And in this case, we only have the Fn, the normal force, times the sine of the angle. Okay? And now we can say, okay, let's see some of the forces for the y direction. In this direction, they are balanced, because it's not sliding down or up the ramp. So 0 equals Fn cos theta minus mg. So I showed you one way to solve it last time. We'll do it a little bit differently this time. We can say Fn cos theta equals mg, or Fn equals mg over cos theta, and we'll substitute then for right there. So mv squared over r equal to mg sine theta over cos theta, or just tangent of theta. Okay. So the m's are going to drop out, and so v squared over r equals g times tangent of theta, or 30 degrees. We can plug in and solve, and v will be equal to about 42.3 meters per second. Okay, and there you go. So these are banked turns. We'll get some practice with this in class. Hopefully this made sense and was helpful.